On your screen right now, you see another example. It says, for each of the following alkyl halides, determine the major product that is formed when the molecule undergoes an E1 reaction. Okay, well, that's great because they're telling me what's going to go on, and this allows my life to be a little bit easier with this example problem. So what happens here is that I need to take a look at the reagents. All right, I'm just going to redraw them. And then here's a bromine group. And I need to show an E1 product. All right, so this is how we do this. This is E, which is elimination. Okay, boop, boop, there it goes. There's bromine, and there's the bond. It goes away. Well, this forms a carbocation, and that carbocation can shift. If it needs to, it can shift. If it goes left-handed, it's secondary. If it's where it is right now, it's secondary. And if it goes right-handed, it's primary. So the carbocation's kind of lazy. It doesn't want to move next door if it's no better spot for itself. So it's just going to end up right there. And that is where the carbocation's going to be. Which means that this molecule is going to go in, this carbon, and form a double bond, either to the left or to the right. All right, so that nucleophile is going to come in, and it's going to go, buy me a drink. And then it either needs to go left or it needs to go right, and the molecule is going to do what's more stable for it. So the double bond is going to form here at that spot. That gives me a more substituted double bond, and because of that, that molecule is more stable. This carbon to the left now has one group. This carbon to the right now has one group. If you went the other way with it, that carbon here on the end, it would just have hydrogens, and that's it. So more internal is going to be better. All right, so there's your E1 product for that reaction. Next one, number 2. Let me redraw again. And then it looks like we have a methyl group that's here, and we also have a chloro group that's there. So E1 reaction is going to happen. Eliminate. So bye-bye chlorine, bye-bye bond. So there we go. So that forms a full-blown carbocation, which is right there. That carbocation can shift in E1. So will it? All right, so this is where the position's at now. Right now, this is tertiary. That's the best for a carbocation. I don't even need to look at anything else because I know delocalization and stuff is not going to play a factor. There's no positives or free sets of electrons or double bonds throughout the molecule. This is it, folks. That's it. No more. So that carbocation is not going to shift. It's going to stay put, and that means that this carbon has to figure out where to put the double bond. Does it go left? Does it go right? Does it go up? All right, so if it goes here, that carbon has 2 hydrogens on that side. That's not the most stable that it can be. And then if the double bond goes here, it's the same story because it's the same group. That's a carbon, 2 hydrogens on the end. There's a better scenario. All right. So if the double bond goes more internal, like here, then that is a better setup for it. So this carbon has a group on it, and this carbon now has 2 groups on it. So more substituted, more stable. And that is what this product would prefer to do. So there you go. There's the product for that E1 mechanism. And that's actually the same product that would happen with E2. There's no difference because the carbocation did not shift. With example number 1, this is what the E2 would give me. There is no difference because that carbocation did not shift. All right? Third one, down here at the bottom. Read that kind of carefully. So it looks like I've got a group here, and then this is actually an I. It almost looks like it continues just a bond down there, but it doesn't. That's an I, and I died, so that I died is going to leave. All right, so in an E1 mechanism, E is elimination. All right, so we'll eliminate the I and the bond. So there we go. And this forms a carbocation at that spot. Will that carbocation shift? If it goes right-handed, well, that's secondary. Where it's at right now, secondary. If it goes to the left, that's tertiary. It's going to want to go to that tertiary spot. It likes that tertiary spot. Ooh, that's the best spot. Location, location, location. Remember that? All right, so I'm going to erase these, erase that. It is going to shift, and that means that the carbocation will go here. And now I've got to figure out where that double bond is going to go. Will it go here? The answer is no. That carbon has 2 hydrogens up here. So that's a possibility. That could form, but it's not the best possible scenario for it. And then if I look left-handed and if I look right-handed, folks, it's the same at this point. So these 2 options are actually the same option. So the double bond is going to form either on the left-hand side or right-hand side. It doesn't matter, but there is the double bond of the molecule. This allows this carbon to have a group, and it allows this carbon to have 2 groups. So I have a total of 3. So there's the product for that E1. Now, this E1 would be a different product than the E2. The E2 would not allow elimination. So the E2 would get rid of the iodine, it would get rid of that bond, and it would form a double bond at this location. That's where it would go. That gives it more substituted groups around those sp2 carbons. But before I go on and do the next one, I want you to take a look at this structure again. Because I just led you to believe that these were different structures, didn't I? Did you catch it? Or did you just accept my word and went on? That's probably what you did. Remember when we first did this example here to the left, and I said, oh, well, the same is going to happen on the left or the right, so we'll do it on the left. What if we chose to do it on the right because I just told you it was the same? What if I chose to do it here? Ding, 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 ding. Look at that. It is the same structure. So no matter which way this goes, E1 or E2, folks, I'm going to end up with the same darn product yet again. And it's just due to turning that molecule around. That's really all that it is. Next, over here, finally, number 4, I'm going to redraw this structure. There's my cyclohexane ring. Here we have a chlorine and a methyl group. An E1 is going to happen. So an E1 means beep, beep. There it goes. Off it goes. A carbocation is formed. That carbocation is at this position, which is tertiary. I don't need to go any further because tertiary is the best. And that means a double bond is going to get formed. Where does that double bond go? Well, it doesn't go up, because that will give me a carbon with 2 hydrogens, and there's a better case scenario. That is one possibility, but it's not the major product. If I go left or if I go right, it is the same no matter which way I go. So let me redraw the top of this again, and we'll do a double bond on the right-hand side. Folks, this is also the same reaction. If a E2 could happen, then this would be the same because there was no carbocation shifts. All right, so there's 4 examples of E1. Those E1s, we need to be thinking carbocations move, and where does it go? That's the same story, the same narrative that we did with SN1. Here's another example. For each reaction, indicate whether a E2 or a E1 will occur and give the major product after you determine that. All right, so let's take a look at number 1. Number 1, I'm just going to go ahead and draw the starting reagent. There we go. And then we'll figure out whether E2 or E1 happens. With number 1, I see bow, 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 bow. Beautiful nucleophile coming in. I mean, the music plays and everything, right? I mean, it's like they walk through the front door and the wind is blowing and you smell the sweet aroma of roses, and you look in the corner and there's chocolate because it's a beautiful nucleophile. All right, so CH3O. CH3O and DMSO. It kind of rhymes. I can make a song out of that and make $1 million, and then I won't have to teach anymore. DMSO, dimethyl sulfoxide, we said that was an aprotic solvent. All right, so CH3O is a pretty nucleophile, and that pretty nucleophile is a strong nucleophile, and that strong nucleophile will be E2. Well, that means there is no wiggle room for rearranging your life, because that nucleophile came in and it did a number on you, and you're going to stay right there, and you're going to have to form a double bond either to the left or to the right, and you're going to form it to the left because that will give you a more stable double bond, more substituents, and there's your product. Next, number 2, again, I'll do this number, redraw the reagent. That's a strong nucleophile. Again, music plays, sweet aroma, flowers and chocolate. That's all you need. So that OH group is going to swoop in. A very strong nucleophile is going to happen. E2 is going to form. That means the double bond will happen where that chlorine is going to be. You just got to figure out where it is, and all 3 choices are the same, so it doesn't really matter. So I'll just form it here to the right-hand side. And there you go. That buddy of yours is going to smack that OH off and say, here's the drink, go away. My friend's going to be single for a while. And there you go. Option number 3. Let's look at this one. Option number 3, and there we go. So CH3OH, I don't see a negative, do I? I mean, this is kind of ugly coming through the door, but, you know, it's there, and I'm going to buy a drink for it so it can go away and leave me alone. So this nucleophile will go in, talk to a buddy. That buddy will buy a drink, and that will rip a hydrogen off from the molecule. So the question here is that it doesn't happen very fast, so it gives you enough time to form a carbocation and allow you to rearrange it. All right, well, does it really need to rearrange? And the answer is no. It's secondary right now. If it goes left, it's secondary. If it goes right, it's primary. There's no reason for it to move. So because of that, that is where a double bond is going to form, and it will go right or left-handed because that will give it a more stable type of double bond. Notice that product number 1 and product number 3 are identical. In one, a E2 reaction happened. In this one, a E1 reaction happened because of that poor nucleophile. But the ending product was the same. No rearrangement went forward here. Same thing. Finally, number 4, down here at the bottom, I'm going to redraw it over here to the left just because I've got a little bit more room. There we go. I'll look at the nucleophile, CH3CH2OH. If an elimination is going to happen and my only choice is E2 or E1, I'm going to say E1. That is a pretty poor nucleophile. It's going to go in, it's going to bother a friend, it's going to get a drink, and it's going to go away. But when it does that, folks, I've got some time to kind of figure out what I want to do with my life, right? I mean, it's not beautiful like I've got to have that person right now. That's going to be my future husband or my future wife. So now that carbocation has formed, we need to think about, does it move? Does it rearrange? If it goes right-handed, this is primary. If it goes left-handed right now, 1, 2, 3, 4, this could be tertiary. But in order for that to happen, a shift has to happen. So the carbocation does shift in this case, but it's got to switch places with something, right? If that carbocation is going to go here, then it's got to switch places with maybe a hydrogen, but there's no hydrogens there. But it does have a methyl group, so we'll get rid of that methyl group, and that's what will trade places with that carbocation. So the molecule really does rearrange in this example. And that is where my new location of a double bond could possibly go. Will it go left-handed? No, that's not the best scenario. It's an option. I do get it as a product. A double bond forms, but that has 2 hydrogens on the end. And then if it goes up, it's the same story. It's the same molecule. There's no difference in that. It's still carbon with 2 hydrogens on the end. So it's going to get a drink from the buddy on the right-hand side. When it does that, folks, this forms an internal alkene that stabilizes the alkene a little bit better, and this is the final product for that reaction. So this E1 did rearrange. It rearranged the entire carbocation and a methyl group. The entire molecule got changed just because of that. And that is the new location of the double bond. Throughout these examples, I do want you to keep in mind this whole idea of cis and trans and E and Z. It's something that I've mentioned before. I'm going to mention it again because it is important. And what you see on your screen right now are basically electron orbiting or electron filling maps of these particular types of molecules. And you can see how much space they're kind of invading into each other with the Z molecule. So Z groups are on Z same side, which means the hydrogens are on the same side, or the high priority groups are on the same side. So here you kind of see that bow in the molecule, and these begin to fight for space. And that's going to create some strain in the molecule, and they just do not prefer that. I mean, they'll be okay with it, but it's not their preferred position. So if they are going to go through this trouble and make a product, they want to make sure that they make a good, stable product. And out of the two choices, this is just not it. The other choice is much better, and this is a trans. So here you see the trans, hydrogens on opposite sides, or the high priority groups on opposite sides. Same molecule, same groups, just different. And notice the structure that this takes on. They're not really invading each other's space. The strain is much less. Yeah, bulky groups are there. That's going to happen. There's no way around that. When you move into a subdivision, you're going to have neighbors. That's just the way that it is. And that's how molecules have to deal with it as well. So this is just something that you've got to pay attention to as far as stereochemistry goes. And this is another image that kind of proves that point. So E's are much better, and trans are much better than the Z's and the S's. Let's look at another example problem. Example. What would happen if we took S2-chlorohexane and reacted it with CH3O- under SN2 and E2 conditions? Oh. Now I see how some of these problems are going to be written. Now we're blending and morphing all of this together. So what this problem is asking me to do is give a product under substitution conditions and give a product under elimination conditions. And they want me to represent both of those. Okay, let's try our hand at this. S2-chlorohexane. All right, so 1, 2, 3, 4, 5, 6. There's hexane. 2-chloro means right there. So this carbon is a chiral carbon. There's 4 different groups on it: a methyl, a butyl, a chlorine, and a hydrogen. And the question is telling me, listen, you're starting with S. That really only plays true as far as substitution goes. That's what we need to pay attention to. But I need to draw it showing an S form. Okay, so this is what I'll do. I'll draw my solid wedge there and my dashed wedge here and dot, dot. There you go. We'll put hydrogen in the back because we can. My high priority group goes up at the top. There's chlorine. And then my next high, because I need S, I need counterclockwise. My next highest group is going to be my butyl. So 1, 2, 3, 4. And then this is a methyl group. So da 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 da. There we go around the rosy. It goes left-handed, which is sinister. So I know in substitution, the substitution reaction is going to give me the opposite of the stereochemistry. So when I do this, when I react it with CH3O-, I'm going to get a product. And that product is going to look like this. Hydrogen, I still keep there. My chlorine, I'll keep it there. There's my methyl group, and here's my butyl group. Okay. Substitution, SN2. It tells me that, SN2. I know it's Sn2 because, look, my halogen's on a secondary carbon. This is a strong nucleophile, so that promotes Sn2 to happen. Chlorine will be substituted with something else, and that's OCH3. There you go. Sn2 does not allow rearrangement. This is the way it is. But I need to make sure that if this started off to be S, I need to make sure that this is going to end up with R, because Walden inversion took place with Sn2. The way that this is organized right now, OCH3 is group 1. My butyl is group 2. So this is still in the S rotation. So how do we fix it? Folks, keep the hydrogen in the back, and then you switch 2 of the groups. 1, 2, 3, 4. And then your CH3, that's going to go there. So now, OCH3 1, butyl 2, methyl 3, and around we go. And there's the R rotation of that molecule. So that's the Sn2 product. But it also tells me, well, you got to promote the E2 product as well, predict it. Okay, so if I predict the product for elimination, I'm going to start off with the same thing. I know that elimination really doesn't care about substitution. 1, 2, 3, 4, 5. I'm missing 1, 6. I know it really doesn't care about Walden inversion and stereochemistry and that kind of stuff. I just need to kind of look at cis and trans. That's really what they want me to focus on, which is fine, whatever. It's okay. So with the elimination reaction, what that means is that E2 will go on. Why E2? Because this is a strong nucleophile. It carries a negative with it. That strong nucleophile is going to look at this product, 1, 2, 3, 4, 5, 6. Here is my chlorine, and it's going to say, boop, boop, boop. There you go. Away you go. There's chlorine off. It's not going to allow rearrangement, so I'm either going to have to go left-handed with my double bond or right-handed with my double bond, and this internal alkene creates a more substituted group for me, so that is a little bit more stable. If I want to talk about stereochemistry here, I can't. Not in terms of R and S, because look, this is a CH3 group. That's not chiral. This is CH with a double bond. That's not chiral. This is a CH with a double bond to the left. That's not chiral. This is a CH2 group. That's not chiral. This is a CH2 group. That's not chiral. And this is a CH3 group. That's not chiral either. The only thing that I can talk about stereochemistry-wise here is around the double bond. So I can show that if they need to, the most stable product, if that's what they want, that's fine. So this carbon to the left has a hydrogen, and it has a methyl group. And the carbon to the right also has a hydrogen, and it has this propyl group that happens after it. So I can show it in the trans notation because this is more stable than the cis. And folks, there we go. There's our product for the elimination version. So Sn2 gives me the product up at the top, and the E2 gives me the product at the bottom. If we wanted to name this, we can. Let's take a look and a stab at this product up here at the top. 1, 2, 3, 4, 5, 6. So this is a hexane. And then at carbon number 2, I have this methoxy group. So 2-methoxyhexane. And then at carbon 2, I have the R group. So that means rotation is right-handed, stereochemistry-wise. So 2R, 2-methoxyhexane. And because there's only one chiral center, I can just leave that off and just write R instead. If you want to keep the 2, keep it. No one's going to scream at you. I'm not. Down below, if we had to name this one, 1, 2, 3, 4, 5, 6. So this is a hexene. At carbon number 2, I have a 2-hexene. And I also can talk about stereochemistry here if I had the option of which one's going to be the best. Trans 2-hexene is going to be a little bit better than cis. If I didn't want to use trans, well, I can use E. That's up to you. Both of those are okay. I know we're comparing hydrogens. Trans is kind of the default, but they want us to get away from cis and trans whenever possible. So I can write E there as well, and it is accepted. So in this reaction, S2-chlorohexane will undergo a nucleophilic substitution bimolecular reaction with methoxide in order to form a product of R2-methoxyhexane that shows Walden inversion and no carbocation rearrangement. Down here below, S2-chlorohexane can also undergo an elimination bimolecular reaction in order to form a trans 2-hexene as a product. That also prevents carbocation rearrangement. In both of these reactions, we are utilizing a very strong nucleophile in the methoxide group, but the methoxide group only goes onto the incoming molecule with substitution. The methoxide group does not go onto the product with elimination. How's that? How is that? See, I can be all fancy when I want to be. I can be politically correct if I want to be. I can talk with sense when I want to. But who would enjoy the class if that's what I did? Right? I mean, you're staring at a screen for 25, 30 minutes at a time, and you're listening to me gab. And who wants to be all prim and proper with this stuff? I don't. That would make for a very boring time. So in the next video, we're going to continue on with the other 3 examples that you see on the screen. So I want you to take a stab at them. I want you to go through and I want you to predict the products of the next 3 reactions. And when you come back, we're going to double check your answers. So S2-chlorohexane, the same stuff that we used up above, but this time under SN1 and E1 conditions. And then notice the last 2 examples. Same reagent, trans 1-chloro-2-methyl-cyclohexane. And in one version, they're giving you SN2-E2 conditions. And in the other version, they're giving you SN1 and E1 conditions. All right, so take a stab on them. See how far you can get with them. And then hit play on the next video in order to double check your answers and to see where you messed up. And I hope that you're going to say, I did. Now give me the A for the class.